Hi, so welcome back. Now, so we were discussing about the effect of when the Prandtl number is small, how do the dissipation effects, viscous dissipation effects, look like, or how do they look like actually? Okay. Now we had from the energy equation. Okay, so we got this equation 4. Okay, we got this equation 4, and you can see that the left hand side, basically, this bit here is actually this bit here actually is the convective term, right? But this convective term, as you can see, disappears, for small Prandtl numbers, right? So there is essentially, if you see the theta bar here, so that is not being convected, right? The temperature change is not being convected, right? Because this term, according to at least to this equation, right, if for a small Prandtl number, the convective terms disappear. So let's just say that for the limiting case, right, where the Prandtl number is very small, the convective terms disappear. The convective terms disappear, right? But, however, viscous dissipation, right, because of the viscous dissipation, there will be a change in the internal energy. Right? There will be a change in the internal energy, and which we basically said, which is basically stems from the very definition of dissipation, as a result of which this will be transferred locally to the wall, right? So you can see that there is no convection of the temperature difference, okay? So, but due to the dissipation, right, there will be change in internal energy, okay, and this is going to be transferred locally, okay, to the wall, right? So there's going to be a change in the internal energy. It's going to be transferred locally to the wall. Okay. Now, so now from what locally to the wall. So, and if that happens, right? If that happens, so if this dissipations, there is no convection terms, right? As we can see from 6 here, right? For the temperature field. So, however, so therefore, there is no convection happening. However, because of the viscous dissipation, there is going to be a change in internal energy, which is going to be transferred locally to the wall. So if that is going to happen, so there is going to be a change in internal energy transferred locally to the wall. So therefore, the adiabatic wall temperature should adequately compensate for it, right? So, when we do that, so that kind of comes up with. So I write out the solution like this, okay. So when that happens, I can actually write okay, which is okay. Now, let me explain this a little bit, okay. So we get this expression, okay. This is like a little bit of a scary expression. Well, there's a lot of math involved in this, okay. There's a lot of math involved in this. Now, Hopefully you remember the this thing that we have talked about earlier. So let me just remind you of that diagram. Right, this one. So we had a plate, okay. So we had a plate, and this x naught is the distance, right, for where the wall temperature is basically the free stream temperature, okay. And it's at x0 it sees a jump where the wall temperature is higher than the free stream, and therefore of course and this is happening why, and the moment that happens, and this is happening because of viscous dissipation. So there is no heat or anything being supplied to the body, but because of that, so there is a jump in the wall temperature which you can see here. So TW, and obviously because of that a thermal boundary layer develops where the wall temperature is higher than the free stream temperature. So therefore because of that I have a temperature difference across the flow which is nearest to the wall here, and it finally reaches the ambient temperature, and this is basically what is my thermal boundary layer. So this is the x naught that we are talking about, okay. This is the x naught, and this is the wall temperature and the free stream temperature, okay. Now so having said that, now from our so constant heat flux, right. So this is a standard solution, okay. This is a standard solution for TW is constant, okay. Now where is 0 obviously, because so this is essentially 0 to x naught, okay. So there's the heat flux is basically 0 because the wall temperature is the free stream temperature, okay. And so when you go past x naught, however, so we have a finite value, okay, this thing. So then the solution, this is a standard solution T wall, okay. So 0 to x, okay. Okay, where I can explain that a little bit, okay. Now if you see here, so basically what we're saying is the wall temperature minus the sorry, so I need to put a sign there. So the wall temperature minus the free stream temperature, okay. Now if you see this term, what does this mean? Okay, what does this mean? This basically means that I am looking at the total change, in the in this heat flux, right? When I go over a small distance, right? In a small distance past x naught, because this is where it's only when you go past x naught, right? That's when you see there is a heat flux which is constant. So this is at the wall, right? So now the point is by how much does that change? So I take a small elemental dx, right, as I go along. So this is my plate as I go along x. I take a small element. So this is the x naught, okay, and this is where I have my flux. Sorry, the temperature jump, right? So when I go past it, I just take a small element dx naught, right? So then I say that this, of course, the heat for that changes. So this is the rate of change, right? And then how much is the total change for the small element dx naught, right, dx naught. So that's what it means, and therefore so this gives you the total sort of flux, and you multiply that essentially by this value, this G function, where this is nothing but Q. So here, you know, so there is a certain distribution of the wall temperature, what you can see here, right. Otherwise, we won't have to do this, we would just say that is QW. You know, so Q end minus Q start. So Q, basically I would have said QW at X minus QW at X naught. I would have said that. But the thing is here, this is a function. This is a function of X naught. Okay, it's not constant. So that's all you do. So this whole term, this thing here, this entire term, this part actually is nothing. It's just summation. It's just summation of the total. So it will boil down to that. So if, and then these two will cancel out. You know, this QW and QW will cancel out. It will remain T wall this, and then basically you're integrating it. Okay, so that's what this integral actually means here, if you want to look at it. So that's what. So that's how, which is what we are using in here. Okay, for our calculations here. Okay, for our calculations here. So this is what we get. Okay. Now the point is that this distribution of this of the standard solution, this is actually proportional to the Prandtl number. Okay, is proportional to 1 by square root of the Prandtl number. So which means that if you look at this, the adiabatic wall temperature minus T infinity. So this is proportional to 1 by Prandtl number. So if I do that here, so then basically I can say, then basically what I can say is that okay, minus that, this, okay. So this thing is proportional to the Prandtl, 1 by Prandtl, 1 by square root of Prandtl. So then I can say it's basically, so I multiply that Prandtl, and the remaining I will just write it as a function of X star. Okay. Now that, so basically I'm trying to get an idea, as to how this actually behaves. So what basically I can see that if, so because of this, you know, dissipation effects, right, if the Prandtl number is very small, then we're going to talk about this a little more on the left hand side of this. So when the Prandtl number is very small, then what we essentially see is that the left hand side, okay, so the left hand side you can see here is the adiabatic wall temperature, okay. The difference in the adiabatic wall temperature and the free stream temperature, right. So the velocity, so the temperature field is essentially a function of, or is dependent on the square root of Prandtl number, okay. Okay, so okay, so having talked about that, so one of the limiting cases that we said, so it does depend, so your, you know, the velocity field does depend on the Prandtl number, and we kind of see what's going on in terms of, so how much, in what way, so that's what is given by equation 7 for the limiting case for the when the Prandtl number is very small, okay. Now the next obvious step to do is to figure out what's going on for large Prandtl numbers, okay. Let's do that. So for what's going on with, what's the case with large Prandtl numbers, okay, that's the logical thing to do. Okay, so in here again, okay, we're going to go directly to the math and then, you know, sort of talk about this. Okay, so if I go to this, these are things that we've been kind of doing for some time now, okay. 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 So right, what do we obtain? What we obtain is y bar okay minus half okay, this is equal to Prandtl number right. So this is what we obtain, and we're going to use this transformation here. So we're going to use this transformation. So we're going to use okay, and y bar is essentially y by right. So essentially this y here okay is y bar into Prandtl number raised to 1 by 3. Okay, so that's what this boils down to. Okay, so if I use this transformation, what we get is the following equation, and you'll see something interesting here. Okay. Okay. Okay, that is equal to okay. So what do we get here? What is, I mean, we use this transformation, right? And we get this equation 9. So what do you think, what is so, wonderful about this? Or, what do we get here? What you see is that this equation is actually independent of the Prandtl number. There is no Prandtl number here involved at all. Okay, so we had this Prandtl number in 8. So if you see, we did have this term here. We have none of that, directly involved. So this is actually independent of Prandtl number. Okay, so we will solve for theta bar. Okay, so when we solve for theta bar, okay, so if we solve for theta bar, we get this, then okay, is equal to okay, so this is what we get. Okay, so if we solve for theta bar, so this is what we get. Hence, from this expression, from this equation, equation 10, what you can see that if the Prandtl number is large, right? So the increase in the temperature, okay? So increase in the temperature meaning, you know, this part of course, right, due to viscous dissipation is quite large, isn't it? So this is for Prandtl number very large, right. So what we can see is that, yeah, for very large, so when this, for this limiting case, right, that when Prandtl number is very large, then the increase in temperature, you know, due to the viscous dissipation is quite prominent, right, quite prominent and considerable actually, okay, for large Prandtl numbers. Okay, so now having done that, so what I will so now what we will do next is actually, so what we will do next is basically now then go and look at a couple of, you know, the cases that we've looked at earlier, for example, for a flat plate, for a wall jet, right? And also how the Nusselt number looks like. We haven't sort of talked about that at all. So what we will go and do, what the next obvious thing to do from here is to kind of talk about, you know, how these things will look like for, you know, a flat plate, and we shall sort of discuss that a little bit, okay, and in terms of equations. So let us see how, you know, that kind of that looks like, okay. So let us say if this is for now a flat plate, okay. Now this is okay for a flat plate, okay. So now we were using this, right. So then we shall use the following solutions, okay. We shall use the following solutions. Okay, so U star, this is as we have been, you know, doing the with the similarity variable, we've been doing this equations with the similarity variable, right, is so V bar is okay, so we'll use this solution, okay. So this is, so let me just, you know, I hope you can remind yourselves, let me, this is what we, and how I got this is from, essentially, I use these, okay. This is just to remind ourselves. So eta is y, this, okay, then u by u infinity is f dash eta, okay, and v is nu v infinity 2x eta f dash minus f. Okay, so this is from where we get this from, okay. Then from 2, which is the energy equation, let us go back and look at from the energy equation, let us go and look at equation 2, okay, which is equation 2. Let us remind ourselves a little bit. Okay. So, this is the energy equation. So, this is the energy equation. So, from this, okay, I am going to write this out. So, from the energy equation 2, what we get is this. Okay, and the boundary condition, eta is 0, theta bar is 0, is 0. Okay, these are the boundary conditions we use. So, therefore, the solution that we get here, so the solution that we get here, which is a function of both eta and Prandtl number, looks like this. Okay. So, that looks like okay. All right, so that is essentially equation 12. Okay, this is my solution. Now, what is interesting here is, so this is the solution that we get. Okay, so we use this transformation into the energy equation. This is for a flat plate, right? This is for a flat plate, and we just come up for now for Prandtl number. Now, in here, for Prandtl number equal to 1, okay. So, from 12, so if that is the case, from 12 what we get, right, Prandtl number is equal to 1, we get, this is the equation to solve for. Okay. So, that it is really that simple. So, it is really this simple, and I mean I have been doing this. I've been showing you how, whether it's the Faulkner-Scan equation, or the Boundary equation that we solved using a similarity variable, wrote down the code and then solved it, and I showed you the plots. So, this is an even simpler equation. Now, there is another thing here. So, this is an important thing I want to talk about before we end this part. Okay. So, now there is this something. So, therefore, that's that. Okay. Now, I am going to write this term here, and then we will come back and discuss this a little more in the next module. Now, this is basically, so as we have been, so this is the non-dimensional field. So, this is essentially the temperature field at the wall, which is a function of the Prandtl number, isn't it? So, from if I solve this equation, of course, so from this equation if I solve, okay, so I will get, so once I solve this, right, for eta at the wall, I should be able to get theta w at the wall, isn't it? So that's what it will be for me if I were to solve this equation. So, when I do that, so this theta wall is basically equal to this, right, and this is R, okay, this, and let us call this stuff as R. Now, I am going to just say here, just write down a few things and then kind of stop. Now, this R, this is actually called recovery factor. Okay, and now for a flat plate, okay, now for a flat plate, this TAD, okay, which is the adiabatic wall temperature, is constant. Okay, in this, it's constant. So it's constant. It does not change along x, which means it is independent of x. Hence, it is also called an eigentemperature. Right? It is also called an eigentemperature. Basically, why eigentemperature? Because that's the temperature, right, which makes the temperature field here TAD minus T infinity, right, it reaches a particular value, right. So, a single particular value. So, let me sort of write that down here. Let me write that down. For a flat plate, right, for a flat plate, the adiabatic wall temperature is constant, right, which is basically independent of x, right. So, and it is also called eigentemperature. Okay. So, we are going to stop here. Okay, we are going to stop here and continue to discuss this a little more in a couple more models. Okay, couple more modules, I mean. Okay, so we will stop here and I will see you next time. Okay, thanks.